for our first example, we're going to compute the flux of the vector field x, y, z out of a sphere of radius a. And so here the out of indicates that we're using the standard positive orientation with the outward normal. Okay, so let's see. The sphere with this radius, so x squared plus y squared plus z squared equals a squared, is a level surface of the function g given by x squared plus y squared plus z squared. So it's going to be orthogonal to the gradient of g, right? Level surfaces are always orthogonal to gradients. And so that gives us a way to come up with the normal vector. So the gradient of g is going to be 2x, 2y, 2z. And then we can see that the normal vector is going to be 2 times x, y, z. So I'm just factoring out the 2 there. And then we have the magnitude of this vector. So this is 4x squared, 4y squared, 4z squared. And then if we simplify that, oh, that thing in the bottom, that's just the radius. And actually, sorry, it's 2 times the radius. And so we have that over x, y, z. And so just 1 over a times the actual position coordinate x, y, z will give us our normal vector. And so that should be right in line with your intuition, because if you've got, here I can even do it in 2 dimensions, then the normal vector at this point is just the vector pointing to that point, right? You just put a copy of it over there, and then I guess you got to normalize by the radius of whatever you're looking at. So let's see. So then if we look at f dot n, that's going to be now, so I'm taking the dot product of this guy with the same guy multiplied by 1 over a, and so that's going to be x squared plus y squared plus z squared all over a, but the top is just a squared, so this simplifies to a. All right, now we're cooking. So we can go ahead and check out the surface integral that we would use for computing the flux. And this is going to be the double integral over S of just A, it turns out, with respect to the surface area element. And so we have A times the surface area of the sphere, which is 4 pi A squared. So we get 4 pi A cubed as our answer. And so we can verify the divergence theorem here. So computing this using the divergence theorem, the divergence of f is going to be, let's see, so we have d dx of x plus d dy of y plus d dz of z, which is just 3. So if we look at the triple integral over the sphere of the divergence of f with respect to dv, this is going to be, see, the triple integral over the sphere of 3 dv, so that's 3 times the volume. Oops, that's radius a, not r. And so again, we get 4 pi a cubed.